we are going to continue to Chapter 5 in Barton-Faulkner and talk about mass transfer by migration and diffusion. So what's the definition of migration and diffusion? Can somebody tell me what migration is? Yes, so migration is movement in an electric field of a charged species, and diffusion is what? Movement down a concentration gradient. Good. Okay, so we have defined this term flux, right? J, big J, is flux, and it has units of moles, centimeters squared per second, per centimeter squared per second. I can define a current. If I have a movement of charged species like electrons or ions, I can define a current equals Z, the charge on the species, times Faraday's constant, charge per mole. So Z is an integer, like -1 or +1, integer charge. F is Faraday's, 96485 coulombs per mole of charge, times A is the area of the electrode, or the cross-sectional area of the electrolyte we're looking in, times J is the flux. So we know what causes flux in both migration and in diffusion. We know what the driving forces are, right? So we should be able to write an expression that describes the flux in terms of those driving forces. And it turns out that there's something very fundamental going on here. The flux in J is proportional, flux J of species J is proportional to the gradient. Do you guys know what this inverse triangle is? It's the differential, but in 3 dimensions. So it's basically a derivative in 3 dimensions. We're going to simplify it to 1 dimension, like d dx. But in 3 dimensions, in Cartesian coordinates, d dx, d dy, d dz, right? So it's basically a derivative. We call it the gradient, mu bar j. So if you think about it, what is mu bar really? This is the electrochemical potential, which we learned about. So what was the definition of the electrochemical potential? So this is the definition of the gradient in 3 dimensions. So these are the unit vectors along the x, y, and z directions. Those are just vectors to define Cartesian coordinates. And these are just the derivatives with respect to position across those 3 coordinates. So, but let's go back to the electrochemical potential. What goes into the electrochemical potential? What are the 2 things that are important? What's the units of electrochemical potential, first of all? Joules per mole. So it's an energy, right? It's an energy. So what are the 2 types of energy that go into the electrochemical potential? Okay, chemical potential is what form of energy? So chemical energy, right? And that has to do with concentration and species type, right? We can define delta G's based on a reference, or chemical potentials based on a reference, and then if you have things at higher concentration, they have higher chemical potential, right? And so what was the other type of energy that went in? How could? Electrostatic energy, right? Good. So you can kind of see here why this equation makes sense, right? So a gradient in chemical energy for a given species is a gradient in concentration. Well, that's just fixed law diffusion. Okay, we'll get there. And a gradient in electrostatic energy, right, is an electric field, right? So if the electrostatic potential is changing, there's a field. So if there's a field, a charged particle should move, right? So you can kind of see why the flux is going to be related to those 2 things. So we won't derive this, but it turns out that the relationship between flux and chemical potential, the gradient in chemical potential, is given by this constant. This is the concentration of the species, this is the diffusion coefficient, this is RT, thermal energy. Take that as the parameter relating the gradient in electrochemical potential to the flux. And this is actually a very, very fundamental equation. It applies for everything. It applies for carriers in a semiconductor. So in semiconductor physics, we often look at what Fermi levels do. This is a Fermi level, okay? Gradients in the Fermi level mean you have an electron or hole current. It's the exact same thing. Okay, so this is fundamental to any species that has charge. And if there's no charge, then it's just a diffusion term. Okay, so it's a really useful transport equation. And then we can add another term, CJV, where this is the solution velocity. And we won't really talk much about this, but this is basically if you have convection, so stirring of the solution, right? You can also move stuff that way. And if we talk about rotating disk electrodes, we might talk about that a little bit. Right now, we're going to focus on this term. So if you remember, mu bar alpha, I is the species, alpha is the phase. So this is just the nomenclature we use to describe the electrochemical potential. And we said that's equal to mu I alpha, so the chemical potential, plus ZIF phi, the electrostatic potential. So again, this is the chemical energy and the electrostatic energy. And then we said mu I alpha, what's that equal to? If I want to break it down further into a standard state term and an activity term. Mu I naught, right, plus RT activity I, right? Okay, so this is basically, you can think about this as like an entropic contribution, right? Because as the concentration goes up, entropy wants to smear stuff out, and it depends on temperature, right? So if you go to zero temperature, right, there's no entropic contribution to trying to smear out having a high concentration. Okay, so that's the electrochemical potential. And so we can just take this and evaluate this gradient. So now we can take this derivative, evaluate just in one dimension, keep it simple. All this is translatable in 3 dimensions very straightforwardly. So let's take the gradient of mu bar j. Let's simplify that to dx, so we're just going to look along the x direction. Mu bar, I'll just drop the j, so it just won't be so specific. And that's going to be equal to dx mu I plus vi f phi. I guess I'm going to keep the i's in there. So that's the definition of electrochemical potential. And dx mu I, so if I just think about the derivative of that, right, is going to be equal to dx mu naught I, which is going to be, what's the derivative of the standard chemical potential as a function of position? 0, right? That's defined as the standard, so that should go to 0. Plus, I should say that whole term that goes to 0, RT ln Ci. And for this expression, we're going to say Ci is approximately the activity of species I, right? So we're just kind of making that assumption to make things a little simpler. And this part equals 0 by definition. And we need to know that dx ln x is equal to what? Equals 1 over x. And dx ln u of x equals, by the chain rule, 1 over u du dx, right? So that's the derivative of a log term, and this is just the chain rule where u is a function of x, right? So we're going to need that here, because c is a function of x, right? Okay, so concentration is a function of x. We take the derivative of something that's a function, function within a function, right? So we need a chain rule. And what we get is that this term here goes very nicely to RT over Ci dCi dx. So I just used this expression, right? 1 over Ci, which is a function of x, right? 1 over u, that's u. So in this case, u of x equals c species I. And then 1 over c is the derivative of the logic. Okay, so this is the diffusion part, right, which needs to go in there, right? So I took the derivative of this term first. So we got to evaluate now the electrostatic term. That one's going to be easy, because if I take the derivative of this, does z depend on x? No, it's integer. Does f depend on x?
No.
Does phi depend on x?
Yes.
Could. Doesn't have to, but it could. So all I need to write is this term. This is just going to go to zi f dv dx, right? We take the derivative of it. So I can now write this whole expression out. D mu bar j dx equals rt over cj dci dx plus zi f d phi dx. We just plug back into our expression for j, which had those terms out front, right? The flux term. So we can all easily do that. We just take this and have to multiply it by those terms we had, which were here. We wrote it negative cj dj over rt d dx mu bar j plus this convection term cj velocity. And then this term we need to plug in, right? This will go in there. And what we get overall is j of x equals negative dj dcj dx minus zi f over rt dj cj d phi dx. The functions of x in there, find, plus cj of x. And this is called the Nernst-Planck equation. And so this is actually the same equation you derive in semiconductor physics. In a lot of different contexts. In semiconductor physics, you definitely don't have this term, because usually your semiconductor is a solid. It's not moving, right? But it's the same physics. And we already mentioned that this is the electric field, Ex. Again, by definition, the gradient in potential is the field. If you think about standing on a hill, the slope, right? The slope of the hill kind of tells you how fast the ball would roll down that hill if you set it there. So let's think about this. We can think about the migration term first. So let's think about the migration term. J, we call that drift. Things drift in a field. They diffuse in a concentration gradient. It's a migration term. We'll just write the same thing again. Z J F over RT DJ CJ D Phi dx. And in an electrochemical context, current far from electrode is carried by drift, by electric field. And the reason is, if you think about it, if you're doing something on an electrode surface, you might change the concentrations locally, and that will set up a diffusion current locally, but you're not going to change the concentration centimeters away from your electrode. And so the only way to have current continuity through your whole electrolyte is to have an electric field drive that current. So primarily, drift drives the current in the bulk electrolyte. And what you want to do is you want to use a supporting electrolyte in our electrochemical measurements, right? We usually use like half molar potassium chloride or something, or a high concentration organic electrolyte. But in the bulk, we want to minimize this term. The amount of potential drop is required to drive the current. Because remember, that gives us the uncompensated series resistance. Remember uncompensated series resistance? So we want to minimize that by using a high conductivity electrolyte to minimize this term. But you can see that here. If I increase the concentration of my supporting salt, right, this term can be very small to support the flux that I need, the current, the ionic current I need. So just to go on here, often we define something called the mobility. Mu J equals the charge number, absolute value of the charge number, F diffusion coefficient over RT. And this mobility, you'll hear this in semiconductor physics too, the mobility is just how fast something can move. So things that are big and massive have low diffusion coefficients and low mobilities. And this is actually an Einstein relationship. It's called Einstein relationship between the mobility and the diffusion coefficient. But often you'll see things written in terms of mobilities in semiconductor physics and in terms of diffusion coefficients in electrochemistry. I can write J drift equals plus Z J over Zj, absolute value. So this is just the sign, right? So this is going to be either positive or negative. This is always going to be positive. So this will basically just tell you is the current going one way or the other. This will either be +1 or -1 depending on the sign of the ion. Mobility, Uj, we use U, Cj times the field, electric field. And if you remember, negative d phi dx equals Ex. So one thing to note, E causes acceleration, right, of species. So if you looked at this, you might say, well, if I have charged ions, shouldn't the ions just keep accelerating, right, in the field? Shouldn't they just keep accelerating? Like if I had a field, right, and I had an ion in vacuum somewhere, right, it would just keep accelerating as force was being applied to that ion. And so how is that related to drift? Well, it turns out that E causes acceleration, but viscous drag applies a counterforce, and we can write the force from the field, Z Q E. So this is the force acting on a charged particle with charge Z, right? The charge of the fundamental charge times its charge number times the field. So this is the force acting on a particle, an ion. And that, when it reaches a constant velocity, a terminal velocity, right? The force from the field is going to be equal to the drag force. And the drag force is given by this equation, 6 pi. Now we're going to have another eta, not over potential, eta a little a s, where this is the viscosity of the solution, this is the radius of particle, and s is the speed. And this is a Stokes, yes, this is Stokes' law. So basically this is just from fluid dynamics. You have a particle moving through a viscous media. It has a drag on it, right? You know that if you try to swim in a swimming pool, you have to put energy out. You don't just keep gliding. You'll eventually stop if you don't keep swimming. And that's the exact same thing here, is the electric field is causing you to swim forward, but the water is pushing you back, and so you just have a constant speed, right? So same thing when you drop a ball from a space station into the Earth, right? You learn about terminal velocity. So the gravitational force equals the frictional drag of the atmosphere on the object. So it's the exact same concept. So that's why basically you can get a constant flux for a given field. A given field will give you a constant flux. Okay, so let's go back a little bit now. In a more formal sense, we'll write a few things down. So we often ignore drift when deriving current potential response. So this has to do with the fact that we often can do this because we have a very high concentration of supporting electrolyte, so that all the current is carried by the motion of those ions, and there's very little field in the bulk electrolyte. Because if you imagined if O and R were charged, which they often are, and there was a big field in your electrolyte, that field might cause them to move too. It might not just be diffusion, but we didn't ever talk about the field when we derived the IE curve, right? And that is precisely because we have so much supporting electrolyte that that field is kept to be very small. Because you have a high concentration of mobile ions that can move, that basically screens any field that might develop in the bulk. So, but there always has to be some, and if you go to very high current densities, it becomes very important, like in an electrolyzer, for example. Or you go to very low ionic strength electrolyte. Like you might not be doing electrochemistry of 1 molar salt, you might be doing it 1 millimolar. Then migration terms become really important. So this is because large concentration of salt, or we call it supporting electrolyte, means the phi dx is very small in bulk. It only really changes a lot of the electrons. And so this is a good assumption when currents are small and you have large concentrations. It's a bad assumption when currents are large or you have low concentrations. And so, in aqueous systems, we often use, KCl, K2SO4, H2SO4, KOH, right? All these typical relatively inert salts. We use buffers sometimes. If you want to work at a constant pH, if you have reactions that consume or generate protons, you want to probably do it in a buffered electrolyte. H3PO4, Na, H2PO4, Na2, HPO4. So basically these different protonation states of phosphate, right? There's these equilibria. They'll set, you can buffer a wide range of pH around neutral electrolytes. And then we also often use non-aqueous, and we'll talk about this in a little bit later, but there we'll often use salts like tetrabutyl ammonium, tetrafluoroborate. So this is a negative here, and this is a positive here, a quaternary amine with the tetrafluoroborate. This is very soluble in like acetonitrile, chloroform, dichloromethane, typical solvents used in organic synthesis, or lithium perchlorate. It's also very soluble in organic solvents. Lithium actually quite soluble cation for organic solvents.